So what are flame tests used to do? What do they help us do? And essentially, or initially I should say, is they help us identify a metal ion within a compound. Because when we heat these compounds, they emit a different or a unique set of colours which mix together and give you an overall colour. So the thing that we see first is flame tests can be used to identify metal ions, as each metal ion will give its own unique colour. Now I'm going to show you some colours. Some of these you don't actually need to know for the specification, and I'll specify which of those you shouldn't really worry about so much. So we'll start off with this kind of top row over on the right hand side here. We've got lithium Li plus ion will produce a red colour, a red flame. You can see that quite clearly from here. In practice, when you actually do these in practice, sometimes it's a bit difficult to see these colours. Some of them are quite faint, but some of them are quite clear at the same time. The next one, sodium Na plus ions. They give you a yellow, or sometimes called amber colour. Potassium K plus ion. This gives you this lilac colour. And it's important that you say lilac and not purple or anything like that. It is really quite important you mention that. And the last two we've got on the right hand side here is Rubidium Rb Plus. It's supposed to be lilac with a reddish tinge. Now I can't see any red in this, but in practice you may see a slight reddish tinge in that colour. Rubidium is not one that you need to know for your specifications. It's just there as an additional example. The next one, cesium, is this bluish violet colour. It's more on the violet, but it's got this tinge of blue in there. Again, it's quite important that we distinguish that it's got a slight bluish colour in it, because otherwise there's no difference between that and potassium. The second row, we've got entirely different set of elements there. Starting off with calcium. Calcium's a 2 plus ion here, and we say it's an orangey red. It does look like a dark or deep yellow, but we say it's an orangey red. You definitely see a red tinge. It's hard to see in this image, but you will see a red tinge in there. So we've got orangey red, or we can call it a brick red. Strontium is Sr2 plus. This is a deep red. Sometimes we call it a scarlet red. And it's a much deeper red than the lithium. It's actually significantly deeper. You can tell a difference. Barium 2 plus is a pale green or yellow green, or sometimes called an apple green. It's quite hard to see this one in practice. I've never quite ever seen that flame colour so visible, but it's a pale yellow, pale green kind of colour. So it's a pale green, yellow stroke green colour. And those three you definitely need to know. Copper 2 plus and titanium, you don't really need to know these two, but again, just there for additional kind of examples. Copper 2 plus is a blue green, and white is silverish. Titanium is this white color with a silverish kind of tinge to it. Again, I've never seen the titanium one, but I can imagine it's just going to look a bit white with maybe a greyish white color. But in practice, you don't really see that, and it's the kind of the 1, 2, 3, 4, 5, 6 that you definitely need to know for your specifications and be able to use to identify the metal ion present in the compound. Now you may be asked also, give the flame colour of some elements that you've not heard of, and if you've been asked that, it's most likely because they don't have a flame colour. So for example, magnesium, one that you do need to know in fact, Mg2 plus, if you've got a magnesium ion and you flame it, you don't get a colour being emitted or wavelength of energy that you can see, and that's quite simply the case. Why you don't see anything is because the energy emitted from the flame test of that magnesium ion is outside of your visible spectrum, so you cannot detect it, but we do have other ways in which we can detect it. And the other thing we need to know is the method of how to do an actual flame test, and I've summarized the kind of the method here. First, we need to clean a platinum nichrome looper wire. So you can see the looper wire here being inserted in. In fact, in this one you've got a splint here, but usually it's something that looks like this glass rod with a piece of nichrome wire looped on the end of it, or platinum. We don't tend to use platinum because it's too expensive. Nichrome's unreactive, we don't want it reacting with anything. So, and it's a lot cheaper as an alternative to platinum. So we first of all need to clean that. We dip it into or concentrated hydrochloric acid and insert that loop into a non-luminous flame. So we just flame it, we clean it off. The acid should dissolve any salts that are on there, but also burn off any excess acid or burn off any substances that are on there too. We then need to let it cool, because you don't put it into the acid again when it's hot, because you end up producing fumes of HCl. You dip the loop into the HCl, concentrated hydrochloric acid, to moisten it and insert it in the sample. That just allows the sample to stick to the loop, so you don't have to try and balance some solid on a bit of looper wire. And then you insert the sample on the end of the nichrome loop into a non-luminous flame. And then you record the colour, and then you clean the loop by repeating step 1. And then you can move on to the next one, but you do need to clean your loop at the end. The reason we use hydrochloric acid, and the reason we tend to use salts of chlorides, chloride salts, so rubidium chloride, potassium chloride, cesium chloride, and so on, is because the chloride ion doesn't emit a wavelength when heated that we can view, that we can see. It's outside of the visible spectrum, so that's why we use chloride. So it's quite important. You do need to know this method. You're expected to be able to describe it. That's quite important. Now, using your eye to deduce whether something's lithium or strontium or calcium, because they have so similar colours, sometimes you may well mistake it lithium for calcium, or lithium for strontium, or strontium for lithium, because they have such similar colours. So we need a bit more of a definitive way of identifying these elements. Now what we can do is we can use a spectroscope. Now a spectroscope is basically like a telescope. It doesn't have loads of gradients in it. It's just a single tube, and it's got a little slit on the end of it and an eyepiece on the other side. And you look down the eyepiece and you point the slit end towards your flame colour, and what you'll see is essentially loads of different colours appear in a bar. Now that shows you, it basically splits that light into all the different wavelengths of light. So a bit like what a prism does. When you put visible light, it refracts the light, so you end up with different colours. In this particular case, that slit is called a diffraction grating, and what it does is it splits up that incoming light into various different colours. Now if you were to point it at white light, for instance, you would essentially get all the colours of the rainbow. In this case, you would get all the colours, all the wavelengths of colours that are mixed together to give you the overall flame colour. So what you will see is something like this. This is what we call an emission spectra. So this is an emission spectra. Because in the flame test, light is being emitted, and it's a spectra because it shows you the range of light being produced over a scale. And we can see some blues, we can see some greens, yellows into reds, almost throughout that visible spectrum. We've got loads of bands of light here of different wavelengths, but this is specific to a particular substance, a particular element. So we can use this as a fingerprint for a specific element, but also compare it to ones that we do have, known, recorded ones, and identify what this unknown gas is. So in a moment I'm going to show you some other spectras, and what I would like you to do is determine what this unknown gas is when you see the other spectras, the emission spectras. It's worth also pausing the video at that point, so you have a bit of time so you can take your time to have a look at and compare what they are. So just as a reminder, this is a fingerprint. It will be unique for a particular element. So potassium will have a completely different emission spectra to lithium, to cesium, to copper, and so on. So because they'll have these unique bands of light being produced at certain wavelengths, and it will be an exact mixture of them. So for potassium, because we see lilac, we're probably looking at more colours towards this end of the spectrum than we are here. And that's something that you need to consider as well. And if we look at lithium, we're probably, because it's red, we're looking at more over here than we are over here, and we expect to see fewer bands. So I'm going to show you the rest of the spectras now. So those are spectras. It's worth pausing the video at this point and seeing if you can identify whether you think this unknown gas is one of these elements. So you should be able to see it. Just take your time, have a look at the bands, and try and just kind of run down the spectra each band to see where the overlap is, and just be careful. Everything needs to appear in the same in that particular spectra in order for you to identify it. So worth pausing the video at this point. So hopefully you've had a look at that and you've identified it as being neon. So neon is the correct answer. Unknown gas is neon. And the reason that is the case is if we look at each of the bands, hopefully we can see this. So we can see that one appears there and there. Probably not good to use yellow, but we're gonna have to highlight in some way. So all of these appear, and they appear at the right places as well. They appear all at the right place. I'm not going to do it for every single one, but you can see that. So for instance, that appears in the right place. These appear here at the right place. Okay, so we definitely know it's neon. It's 100% neon. So let's get rid of those. And it can't be the others because they have gaps. So let's just take for oxygen, for instance, there's a gap in oxygen here, but there's all these wavelengths of light being produced here. So we definitely know it's neon. So I've just added on the side here a few points. So each emission spectra is a unique fingerprint for a given substance. Hence, we can use the emission spectra to identify elements by comparing it to known spectra. So that's quite important. Now, this whole thing is called the atomic emission spectra. So we just put that on the side here, atomic emission spectra. Okay, and what we are going to do in a moment is we're going to look at why we produce these different bands of light and why they're so specific and the same every single time for an element, and hence a fingerprint. And that's something you're going to have to be able to explain quite competently. So one thing we're going to definitely say is we can use them to identify elements, the flame colors, and we can use a spectroscope to help us get these emission spectra. And these emission spectra can be compared with known spectras, and that will help us identify the element. But inadvertently, indirectly, it also gives us information or proves something about the structure of an atom. So that's the next thing we're going to look at. So what do flame tests show us, and more specifically atomic emission spectra? Well, atomic emission spectra prove that energy levels exist. Okay, it shows us that electrons are located in at fixed distances from the nucleus. Remember, the further away from nucleus there are, the higher the energy level. So we could do with a bit of annotation here or correction. So located at fixed distances. So the higher the energy level or energy gap. So it takes more energy to get an electron further away from the nucleus is what it's saying. Right. And the emission spectra shows specific wavelengths of light being emitted. But what does that show as well? So I think what I meant to say there is that how can we prove that those wavelengths of light are being produced? So I've got two diagrams that are going to pop up in a moment, and we're going to have a look at what they mean. So let's show those first. So this diagram on the left, each of these straight lines are energy levels, and we can call them n equals 1, 2, 3, and it goes all the way to infinity. The n is known as the principal quantum number. It's basically for the first energy level, second energy level, and the higher you go, the higher the energy level. One thing worth pointing out here, when we've looked at ionization, and I've seen this on questions before, is that, and I will remove this in a moment, is if I was to ionize an element, so to remove an electron, and I wanted to draw this on a diagram like this, I would draw an arrow going to infinity, and I would put an arrow like so, and that would show that this electron is being ionized, it's being completely removed. However, in this particular situation, we are not ionizing, so let's get rid of those. We're not ionizing these elements, they're already ionized, and we're not looking at removing electrons. What we're looking at them is moving up and down. So when you heat it, so this is from your heat, from your flame, okay, or absorbed light of some form, what happens is that these electrons from a ground state, so we say where these electrons sit normally, that's a ground state, what they end up doing is they end up getting excited. So this electron can move to here, this electron can move 2 stages up, or 2 levels up I should say, and this may move 1. Okay, so they end up getting to these states. Now when they're at these states, they're absorbing specific wavelengths of light which are proportional to the gaps or the differences in energy level. So electrons absorb specific wavelength of light which is proportional to the energy gap between the energy levels. So the higher, the greater the jump, if you like, so this electron here moving 2 energy levels up is going to need more energy than this one here. Therefore, we would start to see that it will absorb a high frequency wavelength, or a large wave, a small wavelength light, in order to promote itself to a higher energy level, I should say. So electrons absorb specific wavelengths of light, which is proportional to the energy gap between energy levels. These electrons have been promoted. So worth just writing, so these electrons have been promoted to an excited state. Now basically it means they can't stay like that forever. So when you are heating it, these electrons are spontaneously moving up to the relevant energy levels, but they won't stay there for long. So here on the right hand side are my excited electrons. Now what will happen is they won't stay there for long, so they'll start dropping down back to their ground state. So I'm going to use some straight lines to make it nice and neat. They drop back to their ground state, so this electron will drop down to n equals 1, principal quantum number 1. This electron might drop back to here, and this electron back all the way down, just as before. So let's just put some arrows in to show the direction. And as they do that, so let's focus on this one here. That's quite a big energy gap. So as it's dropping down, it will emit a ray of light, a specific wavelength of light which is proportional to the energy gap. So it will now emit light, and we'd expect that to be on the high energy end, so we may be towards the blues and purples, whereas this may be towards the red end, and this might be somewhere in between, so like the green and the yellows, if you like. But we don't know, we don't have a way of telling here, but it will be essentially somewhere in between these two. And it's that mixture of light which gives us our flame colour. A unique blend of specific wavelengths gives us our specific colour, which we can then use to identify this element, but also it's the ones that we pick up on the spectroscope. So what we'll see is essentially these waves of light coming off from those electrons dropping down back to ground state. So I'll just move that over so you can see those arrows. So like the green could be the first one on the left, electron dropping down. The red might be the one only dropping down from 3 to 2, and the one dropping down 3 to 1 might be my blue. But they are proportional. So electrons, what they will do there is the electrons will move back to their ground state, and in doing so they will emit, let's get rid of that, will emit a wavelength of light, or frequency of light, you could write here, which is proportional to the energy gap of the two energy levels. And it's that mixture of wavelengths, so it's the mixture of wavelengths we see in a flame test. Right, so how does it prove that we have energy levels? Well, it proves that we have energy levels because the electrons, when they are dropping down, or they are emitting specific wavelengths of light, which we know they do by using a spectroscope. And those specific wavelengths of light, it takes a certain amount of energy to get electrons to be excited. Okay, this electron will absorb a very specific wavelength of light to get up to that excited point. But as it drops down, it will specifically emit that one wavelength, and the same happens for the other electrons. So that means that the electrons must be moving through fixed points, fixed distances. So it proves this idea that we do have energy levels. Okay, it proves that in order for these wavelengths to be present or being emitted, that the electrons dropping down must be producing these wavelengths, and they must be producing these wavelengths because they are dropping down via fixed distances. So the smaller the distance, the lower the energy light that is being produced, so towards the reds and the yellows and greens, if you like, and then the blues and purples are the higher energy. And each element will have a specific pattern of electrons, which they will always move up the same energy levels and drop down the same energy levels to get back to ground state. So that's really quite important, and therefore we get these fingerprints of each of these elements to help us identify them. So it's really quite a key thing that you need to be able to explain and understand, and I hope that makes sense of why it shows or proves that we have energy levels.